What is CAMG? That is the topic of today's discussion. CAMG stands for Computer Aided Modeling Program with Graphical Interface. That's what CAMG means. And this program works with MATLAB. And the CAMG delivers the computer models to MATLAB in such a way that MATLAB can perform the simulation. So in that way, it's a modeling software and like a preprocessor. So let's examine the details of this. So this is a package that's computer integrated and this for the simulation of physical systems. So let's look at the process here that we use in modeling and where CAMG fits and what it is. Yeah. So in here you have a bone graft model here. No, a physical system. Then we create a sketch or call engineering model, and then we make a one-to-one relation between the physical system and the symbols of bone grafts. And what CAMG does is it takes this bone graft model and produces the input files for several programs like ACSL or MATLAB, and then these simulation programs would produce the data and the tables that we need to perform our calculations. So in here we have the what are the steps that we normally use to model something. I took this approach from Norman Neese, who is an author for the Control Systems book, and summarized the steps of doing a model. One is determination of a physical system and the specifications, the requirements. Then draw a functional block diagram. So before you do this functional block diagram, you have to have the equations of motion of the system. Otherwise, you cannot do it because block diagrams represent equations. You want to transform the system into some sort of an schematic and then use this to obtain a mathematical block diagram that has the representation of the equations. So the first one was like, the functional block diagram, what parts are connected. But the second one is really a block diagram from the equations of motion. On number 5, reduce the block diagram to a closed loop system, and then of course you do the analysis. On the CAMG MATLAB approach, you identify the physical system elements first. You may use word bone graphs so that you can describe how the system is connected. Then you draw a bone graft model that using CAMG describes the system that you have, and then turn CAMG to set it up in such a way that we get a MATLAB input files, and then just use MATLAB to do the simulation. That's the idea. So here we have some very basic principles. Like on the left, we have the differential equations that control the dynamics of the circuit and the corresponding second-order differential equation. The one on the right shows us the differential equation of a mechanical system that in this case, if you compared to the electrical system, the form of the derivation of the equation is different. In one case, we use the Kirchhoff's laws, and on the other ones, we use Newton's laws. Nevertheless, both systems produce differential equations of second order. From those equations, you could transform it into first order and get a state space form. Or you could directly describe these equations to Simulink, do using double integration, and then you get the result. Or like I said, you reduce them to a first order like you see over here. This is the circuit here, and this is the mechanical system. The point of showing you this is that the circuit on the left hand side on this picture has the same differential equation, the same format of the differential equation as the one on the right. Both of them are in two different energy domains, and therefore the equations are going to be different. But that's as far as they're different. The form of the equations are the same. So, and it shows also here, if we transform them into two first order equations, you can see that the state variables here are Q and I, and on the second one you have X and V, and both of those are equivalent systems to the second order differential equation. Now, what CAMG does is it has the ability to help you enter these bond graph models into the computer. This bond graph model represents each one of the elements over here. Like this I element represents this inductor, the C element represents this capacitor, the R element represents the resistor. And the same way on the right hand side, before we go to the right hand side, notice that there's a common current that is a common variable to all three of those elements. On the right hand side, the velocity is common to all three. But you see, when you say current on the left and velocity on the right, those two variables are like in the same type of variable, same family of variables. And so in here in the mechanical system, we end up with the same bond graph, but we did not, get the mixed up both of them. They were derived on their own. So happens that the way they are connected and the elements that it has, it coincides, and therefore the bond graph models look the same, but the units and the meaning of each one of the variables is different. However, it illustrates the idea that using bond graphs, you could represent systems in many energy domains: electrical, mechanical, hydraulic, thermal systems. This is the idea. The computer will deliver the equations to MATLAB in the Cauchy form, which is the explicit first order form, or it delivers them in this form called the state space form. In state space form, you have that the derivatives are on the left hand side, and then there is a matrix here, which is the A matrix. And then you see that vector where you see X and V. That's called the state variable vector. And then you have a vector of inputs. So that's where you have F. If we go back over here, for this example, you see that what are the necessary variables that we have or that we need rather to describe the system. Obviously, to describe the position of, the status of the entire system, we would need to find the position of the mass. That's very obvious. But as it's moving, do we need to know anything else? And the answer is yes. We also need to get the velocity here. So you have a situation where you will determine the velocity of this. Sorry. The velocity of this or the current on this other side. But here you can enter that bond graph model into CAMG, which is what you see here. Once you put into the CAMG, you could examine the equivalent block diagram if you like, or you just produce the necessary bond graph model input for MATLAB. And that's what's happening here. This is what we entered into CAMG. We enter this, whether it is for the mechanical or the electrical system, it does the same way. Okay, so at this point it's important to point out that what have we achieved? Where do we want to go with this? First, we generate a schematic model of real life, and then we create the bond graph model. And then once we do that, and we're here, the CAMG software is going to do those three things for us. Actually, that's more than that, but I mean, this is what we need at this time. It will automatically derive the state space equations. It will do the symbolic system matrices that those equations require, and will perform the simulation using these M files in MATLAB. Okay? And then once the model is generated, you have to add or enter, I would say, rather the physical parameters, the control blocks, and everything. Once you put that into the MATLAB file, the M files, in this case, it will deliver it for the CAMG-SYM file, which is the stand for CAMG symbolic file. So in here you have that you can do it in the frequency domain or you can do it in the time domain. And then you'll get the numerical results. That's the idea. So you'll have in very brief, you'll have the generation of the bond graph model and then automatically generate the equations, and then you'll be ready to do your simulation. Okay? This is words, what we have reduced to. Create a bond graph model, produce the MATLAB M source file automatically, and now we can produce the transfer functions for each output chosen. Okay. And finally, model the physical and control system. Combining block diagrams and block diagrams, you could use Simulink. How does the equations of that CAMG produces looks like? They look like this, and they are based on individual constitutive equations, but they are related to one another in such a way that form a system of the equations in the Cauchy form. This is in the individual elements form, but we can have it in the state space form or on this form. CAMG generates these files. The mod file, which is the model file, the equations file, which is the differential equations file, and then the CAMG-SYM file, which is the symbolic file. Also, you have a CAMG num file, which is just to work with numbers, not with symbols. This is a view of how the first file, the CAMG mod file, looks like. And then this is the input for MATLAB. In the example that we saw a moment ago, and here you have a description of the physical parameters, what the inputs are, the initial conditions, the time control, the solutions of the equations, and of course doing some plots. So that's in a nutshell, it goes from beginning to end, producing and setting up computer models. Okay, this is the description of the physical parameters here. These ones, right there. The external inputs. And then you have the solution of the equations by using, you call this statement here calls the solver of the differential equations. And then of course a matter of plotting what you see. In this case, the CAMG-QU file produces the equations in individual form, and this is used mainly for the time domain. But once you submit those files to MATLAB, you will get a response like this. This is a time domain response for the displacement. So at the top, you're going to see the velocity, and at the bottom, you see the position. And that we can do with many other variables.